We can calculate the torque. The torque, if you recall, is F times R. And so it's going to be F1 times A over 2. Don't worry too much about this derivation. You have the final equation for torque on your equation sheet, which you do need to worry about. But as far as this derivation, I just want to show it to you. So that's the force times the length of the moment arm plus F2 times A over 2. So that's going to be I times B times B times A over 2. This is just the force, which we had before, plus I times B times B times A over 2. Just the force times the length of the moment arm. Torque is equal to F times R. And so this is equal to I times B times AB. All right, but this A times B, if we look back at our figure, that's just the area. And so we can get this general formula for the torque of a coil of wire in a magnetic field. The torque is equal to the magnetic field, or excuse me, the current times the magnetic field times the area. You can go back up. We clear? This little dark blue spot right here? You can't read that? That's an A. I'm sorry. I think I made it into a capital A. Yeah, this is the force, IDV, A over 2. A over 2. Yeah, those are A's. Sorry, you were supposed to take a course in Chad in the languages department before you came into this class, but I guess you missed that prerequisite. All right, I'm sorry. So also, if we have multiple turns of wire, this was just for one turn of wire, but I think that you can imagine that if I have multiple turns of wire, N, then this torque is just N times I times B times A. Or as I can say, it's NIPA. Right. So if you have a coil of wire, we did this for a rectangular coil, but it's also true that if you have a circular coil, which is usually what you have, this is called the armature of an electric motor. If you have a circular coil, it's still N times I times B times the area, so pi r squared for a circular coil, or whatever type of coil that you have. This is on your equation sheet. Notice it's related to the current. So more current, I get more torque. It's related to the magnetic field. More magnetic field, I get more torque. More area of my coil, I get more torque. And if I have more turns, I get more torque as well. Let's try this quick test, and I have a little video I want to show you. I want to know in which direction does the loop initially turn. So you have this loop inside of a magnetic field, and I want to know which direction does the loop turn. At least initially, and then we'll talk about what happens after that initial turn. Which direction does it initially turn? So think about the direction of the magnetic field. We know which direction magnetic fields go from. And then think about what force is caused on that torque, that coil of wire. I'm going to stop at 1 minute. 1 minute. So you have about 8 seconds left to get in your answer. Just a few seconds. Okay, so looks like we're a little bit divided. So the first thing you want to do is say, my magnetic field is in this direction. That's the direction of my magnetic field. And then you just take one side, and you say, well, let's take the left-hand side. My current is out of the page. The magnetic field is to the right. And so my force on that side is up. The force is up on that side. If you do the same for the opposite side, the current has just switched the opposite direction so that it would be down. That makes the coil will turn in a clockwise direction. So I have one force going up one force going down, I'm going to twist that thing, and it's going to move in a clockwise direction, at least initially. And we'll see what happens. This is a type of electric motor, and we'll see what happens with electric motors and how they deal with this. So, as the loop rotates, the force changes directions. And when the coil has rotated a full 180 degrees, like if we imagine up here that what if my current was in this direction and my current was in this direction? That's after a rotation, right? That my currents now will be swapped and the directions will be flipped, the directions of the current, because this side will be over here. Now when the force was up, now the force is going to be down. So that's not very useful for an electric motor. Right? You've seen electric motors before, what they do. They don't do this. They don't go back and forth. But what we've just built here is a device that's going to go this direction, and then when it changes, when it rotates by 180 degrees, it's going to feel forces going the opposite direction. So what you'll get is a device that goes back and forth, back and forth, back and forth. And that type of motion is kind of hard to harness to drive, a vehicle or whatever it is that you want to do with it. Because you want continuous motion that continues in the same direction. And so, as the loop rotates, the force changes direction. And when the coil is rotated 100 degrees, the force changes directions as well. In electric motors, then, you have to change the direction of the current after each revolution to keep the loop rotating in one direction. So what you want to do is, as it rotates, you want to keep that current, you want to flip the direction of the current in order to make it keep rotating in the same direction. And if you can do that, then you can have an electric motor that will continue to go in the same direction. And so a couple of things you can do. You can use a type of switch that changes the direction of the current. This is kind of like those double pole, double throw switches that you've been using in lab. If you've done the tangent galvanometer, you use the double pole, double throw switch, the black switch, but you can go either direction. That changes the direction of the current. And electric motors use a similar thing to that, a type of switch that changes the direction of the current. And these are called brushes. You might have heard of that you have to change out the brushes on your motor. That's what they do, is they change the direction of the current every half revolution. And they're used in DC motors. That means direct current motors, the type of current that we're talking about, where the current always has a constant value. It's always plus 2 amps or whatever it is, happens to be. The other alternative is that you can use alternating current. That is AC electricity. And this actually, the current goes back and forth at a set rate. Now these motors have to operate in a particular way. Usually at 60, this rate is at 60 times per second or 60 hertz. You might have seen that number on some of your electrical devices. It's referring to the frequency at which the alternating current switches back and forth. And that value is important because it sets the parameters for your electric motor. Let's see. I want to show you a couple of things. This is a little hand crank generator. You ever seen one of these? This is just an electric motor, really. It's a generator. It has some gears here that hook up to a coil of copper wire inside this thing. It's really a little motor. And then that's attached to this light bulb. Are y'all ready to be illuminated? That's pretty cool, right? I can create electricity just by moving my hand. And in fact, this is how all of our electricity generation works. That we have something that spins a fan, a turbine, and then we use that mechanical energy to move a coil of copper wire that sits inside a magnetic field, which generates an electrical current. we can move that turbine in a lot of different ways, right? What are some ways that we move it? Huh? Hydroelectric, like we have a big dam and we hold the water back and then we let the water through and turn the turbine. Right? A lot of people like, especially out west, but they have a lot of big lakes to do as well. Around here, more common is what? Heat, right? We use various sources of heat. Natural gas, we don't use coal so much. Nuclear energy, that's just a way of heating up the water that will produce steam and turn those turbines in order to move a coil of copper wire which generates an electrical current. We saw that before with electrical generators. All we're doing is basically the opposite of an electric motor. An electric motor is really just an electric generator in reverse. So your generators that you use during hurricane season or whatever, they're just like an electric motor. They have a big coil of copper wire that sits inside of a magnetic field. You crank up that gas engine, and all it does is it spins that copper wire. It has an axle that spins that copper wire, and it generates a current. We did this in Olympiad recently. Science Olympiad, many of y'all worked this. This was the wind power event. And so what students are supposed to do is they create some device like this. They create a device like this. This one, the students left behind because it did very poorly. Like it actually didn't spin at all at first. You put it in front of a fan, and then you want it to spin, and then you have to measure the amount of current that comes off. This is like a wind turbine. Y'all ever been out in West Texas? West Texas? They have those big farms, those big wind farms with these huge windmills. That's all this is. It's just a little electric motor that's designed to operate in reverse. So that when you spin it, you get an electrical current out of the terminal. Put these on there. All right. So that is an electrical generator. Look, I have two of these actually. I'm going to show you something that's kind of cool. I can hug up a little wire here, and instead of lighting a light bulb, it'll also put a current through this wire. So I have this one, and watch, I have this other one. If you don't believe me that they're really just the opposite, you sort of hold that above your head so you can see it. All right, so I'm going to spin this. What do you think is going to happen over there? It is pretty cool. See, because I'm providing an electrical current to this one, which then drives the electric motor. Isn't that cool? So an electric motor is just an electric generator. They just operate in reverse. I have we'll come back to this and sort of catch up on that generator, but I have a video that I want to show you. So we sort of talked about this before, but if I move a wire through a magnetic field, then I want to know what is the direction of the current in the wire. And so I can sort of think of this wire as having protons in it. And so as my wire moves into that magnetic field, those protons are going to have a velocity to the right, and they're going into a magnetic field that's into the page. So these protons, as they move through this magnetic field, are all going to move in the upward direction. So they're going to feel a force that is up, causing the direction of the current in the wire to be up as well. So the current in the wire will have an upward direction due to the force on those charges. Remember, we talk about the flow of electricity as the flow of protons. Even though it's not, it's really the flow of electrons. And so in that way, the generator, it just works the same way as the electric motor, except you provide the force and the generator produces the current, as opposed to the opposite where you provide the current and the generator provides the force. All right, let's look at the cyclotron, the mass spectrometer. Some of you might have used this in some of your chemistry classes if you've taken some upper levels yet, or you might if you go into graduate school in biology. But if I have a charge moving in a magnetic field, the force is perpendicular. That causes a centripetal force, which causes the charge to move in a circular path, like we've already seen. we can measure the radius of that path, will tell us something about the charge. So let's consider this first. I have this charge moving through this magnetic field. This charge actually is going to move in an upward direction. Well, let's imagine, though, that this is a negative charge. So instead of a positive charge, let's say that it's negative, then that charge will move in a downward direction. Right? Because remember, with negative charges, you have to take the opposite of what the right-hand rule tells you. So here, it's moving to the right. The magnetic field is into the page. I get an upward force, but since we're saying it's negative, then the force will be downward. And so my force on this negatively charged particle is down here. Over here, the force is going to be in that direction. Over here, the force will be in that direction, and on, causing that particle basically to get stuck in this loop. If you've ever heard of cyclotron radiation, that's what cyclotron radiation is caused by. I'm not sure if you've ever heard of that. It usually happens in space, but we can get it in a lab too. When an electron gets caught up in a magnetic field and it moves around and around and around like that, it will emit radiation. It'll emit photons. All right, so the direction of the force on this particle is down, at least initially. But notice the force changes as the direction of the particle's path changes. We can write the particle's force by this, that F equals QVB sine theta, but sine of 90 is equal to 1. And since it acts as a centripetal force, we can say this. Now remember centripetal forces, guys. Centripetal forces aren't like a separate force. A centripetal force is really just a label that we give to a particular force. So for example, a car going around a curve, the static frictional force is the centripetal force. Our ball on a string, the tension in the string, that is the centripetal force. So in this case, the magnetic force is the centripetal force. So we say QVB equals mv squared over r. If y'all recall that from last semester, the centripetal force is equal to the mass times the centripetal acceleration, which is v squared over r. You don't necessarily have to know this, but you do need to know what the cyclotron equation is and then how it comes about. So you do need to know sort of where this comes about. This gives us the cyclotron equation. You can write it in this form, or you can write it and solve for r. If I solve this for r, let's see, I get rid of those. R is equal to mv over qb. So in a mass spectrometer, all you're doing is you're measuring the radius and then using that to identify the mass to charge ratio. Because you set what the magnetic field is, and you also set what the speed is. And if you measure the radius that path of particles follows, then you can measure the mass to charge ratio. So let's do this example. I have this particle. It has a speed 1.79 million meters per second in a magnetic field. And then I measure the path of the particle to have that radius, 0.16 centimeters or 0.16 meters. And so I measure, or I calculate then, what is the mass to charge ratio? It's going to be 0.16 times B, which was 0.35, divided by V, which was 1.79 times 10 to the 6th. And I get 3.13 times 10 to the negative 8. Now that's the units of that are mass to charge, so that's kilograms over coulombs. But then I go and I say, well gosh, I know the masses and charges of all these different particles, and I can go through and they have fairly disparate mass to charge ratios, and so I can pick out what is this unknown particle that I just put through my mass spectrometer. And this unknown particle happens to be tritium, 3 hydrogens, because the mass to charge ratios match up. I would expect a problem similar to this. We'll do one to practice. I think there's one on the next page. Yeah, I would expect one similar to this. I want you to know how a mass spectrometer works, and then also how to calculate or how to determine the mass to charge ratio. So let's try this one. It's a quick test. What is the particle in this case? Once you find the mass to charge ratio, you can probably just look at the, what are these called? The numbers in the front. It's like this one's about 1, this one's about 2, this one's about 3, and this one is also about 2. You can sort of estimate. You can go through and calculate the mass to charge for each one. Let's try to wrap up in about 15 seconds. So we're going to go to 215. 215. So 5 more seconds. Look at that. That's awesome. So you measure the mass to charge ratio, M over Q, which is equal to RB over V. R is 0.052 meters. B is our magnetic field, 0.4 Tesla. And our speed is 2 million meters per second. And that gives me a mass charge ratio of, you might know, I mean, most of you, 56 of you know, what is that? 1.2? All right, yeah, and as I said, you can just look, that has to be hydrogen because these are the only ones that will give us a ratio of 1. But you can double check that if you want. So A is the right answer. Is that what I put? Yeah, A is the right answer. Very good. I've been reading this book at home. It's on anti-gravity. Can't put it down. What will you do when you don't take physics anymore? Get your jokes from the internet, I guess. All right, let's do some more clicker questions. Oh man, you were looking, you saw the answer. All right, which of these particles, I have these particles, they both originate here. One of them travels to this detector, one of them travels to this detector. So they have the same mass and the same speed. I want to know which of them has the bigger charge. Which has the bigger charge? All right, let's stop at 1 minute. It's 5 more seconds. I think B is right. Let's take a look. So we know our cyclotron equation. R is mv over qb. So I want to know which one has the bigger charge. If I make Q big, that makes R small. So the bigger charge is the one that has a smaller radius, and that is indeed B. So B is right. Because if Q is bigger, R is smaller. That comes about from the cyclotron equation. I think these X's are into the page. I think y'all can see it better on your page. But I have this particle that comes in, it's a proton, and goes into this magnetic field, which is into the page. What happens to the kinetic energy of this proton? We haven't said this explicitly. It's something we talked about last semester, but you think about it. what happens to the kinetic energy, and what does the kinetic energy measure, and how is it going to be changed by this magnetic force? Is it going to increase, decrease, stay the same, or D or E? All right, let's stop at 1 minute. 1 minute. I'll go to 103. Hey, that's pretty good, actually. C is right. I don't know if you recall this from last semester, but we said centripetal forces, they don't change kinetic energy. Because you know what? They don't change the magnitude of the speed of the object. They only change the direction. And that's true for magnetic forces. They also only change the direction of the particle. They don't change the kinetic energy. Here I have a beam of electrons. They're traveling through an electric field. So think about what is the direction of the electric force on those electrons. And then I want to bring in a magnetic field that will cause the electrons to go in a straight line. So there are a couple of things that you need to do here. You need to first determine, well, the electric field is up. Will the electric force on this beam of electrons be up or down? And then, whatever it is, up or down, you need to figure out what magnetic field will give me a force that will oppose the electric force. This is pretty common in devices, that you have a magnetic field and an electric field that you modulate that allow you to move a beam of charged particles in one direction or another. The TV used to do this back when we used to have those big TVs. You ever had one of those, like in the big wooden cabinet, you have to bang on the top of it? I don't have one of those. I guess it's just Mississippi, right? Is that right? What? Oh, okay. Your grandparents. They were from the... Megan, did you have one? Anyway. The cathode ray tubes, the big computer monitors, those have a beam of electrons that are modulated by an electric field and by a magnetic field. You change one or the other to move the electrons around. Anyway, back to this question. So, that's all. Let's take a listen to this. Let's stop at 155. 155. That might be right. I have to see. 155. I'm not sure. Let's take a look. So, I know that my electric force on a beam of electrons is up or down. It's not up. I appreciate that. But the electric force, you know, a positive particle feels a force in the same direction as the electric field. Okay? So a negative particle will feel an electric force that's opposite. I know what you were thinking. You were thinking the force is the same direction as the electric field. But it's very important here that it's an electron. So the electric force is down. So the magnetic force has to be up. So if our magnetic force is up, we do that whole thing where we say, well, God, V is in this direction. The force has to be up. So my magnetic field has to be into the page. But it's electrons. So I take the opposite. So it's not into the page, it's actually out of the page. What y'all got? Look at you. Many of you got. What am I going to do when y'all leave? What about the next students next year? It's going to be sad. Okay, let me step back through that again. First of all, you ask yourself, what is the direction of the electric force? The electric force is down because it's in a negative charge, and it's opposite the electric field. And so then, I know my magnetic force has to be up. The speed is in that direction, So my magnetic field should be into the page. But wait, you say, because it's an electron, you just take the opposite of whatever answer you're looking for. So it's out of the page. So the answer is D here. I want you to take out a sheet of paper. Pop quiz. No, we're not doing pop quiz. We're doing a midterm assessment. So on a sheet of paper, with or without your name, I don't care. I like to do midterm assessments because you'll do an assessment at the end of the semester, but it doesn't really impact you at all. And so at this time, I'd like for you to, on a blank sheet of paper, with or without your name, write something that you like about the course and something that you would change about the course. And, you know, within my ability, if I can change it, I will. So something that you like about the course, and then also something that you change. And then if you could just sort of set it up here, face down, on your way out.